Hello students, welcome to my YouTube channel Integrated Physics Studies IPS. एथरे मु ऑलरेडी प्लस 2 सेकंड ईयर सिलेबस कंप्लीट कर सारछि एबे मु प्लस 3 सीबीसीएस ऑनलाइन क्लासेस रो वीडियोज गुडा अपलोड करिवि जदि भल लागिला ताले लाइक कर देबो एवं सब्सक्राइब कर देबो जो वीडियोज गुडा मु अपलोड करिवि तार नोटिफिकेशन पई एठी बेल आइकन को ऑल रे सेट कर देबो गोटे इंपोर्टेंट जिंस वीडियोज रो ऊपर एठी जो 3 डॉट्स देखुछो तार क्वालिटी एठी देखो बाय डिफॉल्ट 360 अछि तमे ताकू पढे मध्ये परिबो एठी एडवांस रे क्लिक करी तमे रिजोल्यूशन बढ़े परिबो प्रति वीडियोज रे मु पीडीएफ लिंक देबी ताकू एठी ड्रॉप डाउन लिस्ट रो तमे क्लिक करी डाउनलोड मध्ये करि परिबो पीडीएफ को लास्ट रे एठी जो मोर चैनल नेम अछि याकू क्लिक करी तमे एठी प्ले लिस्ट को जाई मु प्रति वीडियोज को यूनिट वाइज एज पर सिलेबस सजाई की रखिथिबी तमे सर्च करि परिबो ओके थैंक यू हेलो स्टूडेंट्स आज रो टॉपिक रे हमें स्कैनिंग टनलिंग माइक्रोस्कोपी विषय रे पढिबा व्हिच इज इन शॉर्ट STM, and actually it is a type of scanning probe microscope which was developed by two scientists Judd Binning and Henrik Rohrer in the year 1981, and for this invention actually they were awarded the Nobel Prize in Physics in the year 1986. Now an STM can produce images having lateral resolution of 0.1 nanometer and depth resolution of 0.01 nanometer, so it is having a very good resolution power. Now it is capable of imaging and manipulating individual atoms within the materials. So if we see the working area of this STM, it is capable of working in various conditions. Okay, STM can work in ultra high vacuum as well as in air, water and various other liquid and gas ambients, along with a very wide range of temperatures ranging from 0 degree Kelvin to about 1250 degree Kelvin, and it is having a scan range of typically up to 1 micrometer with a scan speed of the order of few per minute. Okay, so this means the STM has a capability of scanning 1 micrometer area with a scan speed of the order of few millimeter per minute, right? Now let us see the principle of STM, which is based on the concept of quantum mechanical tunneling, okay, which we have studied in the application of Schrodinger equation. So the scanning process is carried out by a probe that monitor the electrons which tunnel between the surface of the specimen and the probe tip, and here the specimen is the sample. Okay, now the basic principle of the STM is sketched in the figure, and the scanning tunneling microscope is actually utilizing a wire. Okay, as you can see in this figure, it is utilizing a wire with a very fine point or tip. Okay, now since multi-wall carbon nanotubes, that is in short MWCNT, okay, or MWNT, so this is your multi-wall carbon nanotubes, and it is utilized by your STM, which are electrically conducting, so they may be used as the probes for the STM, and this tip is actually positively charged and it acts as a probe. Okay, now when the separation between the tip and the sample, okay, is about 1 nanometer, then the electrons at the individual surface of the atoms are attracted to the positive charge because electrons are negatively charged. Okay, so they are attracted towards the positive charge of the probe wire and they tunnel, means they jump into it. Okay, so in this process a small tunneling current typically is created, which is in the sub nano ampere regime. Okay, so as your electrons are charged particles, so obviously if they move they will create current. Okay, and this is a very small amount of current having sub nano ampere regime. Okay, so if we try to understand it in figure, so you can see this is the sample which is connected with the positive of the tunneling voltage. Now this is the tip and the separation between the tip and the sample is about 1 nanometer. The tip is connected through a wire as we have discussed, which is thereby connected with a tunneling current amplifier. Right. Now there is a piezoelectric tube which is holding this tip. Okay, and this tube is having electrodes and its voltage can be controlled. Okay, now apart from this there is a distance control and scanning unit. So when this small area is scanned because of the tunneling of electrons, then it looks like this. Okay, so this is the small area where you can see these are the atoms. Okay, arrangement of the atoms, and it can be displayed through this monitor. Okay, this is a data processing and display unit. Okay, this is like that of a monitor. Okay, so this is the principle as shown in the schematic diagram. Now if we see the mode of operation of scanning tunneling microscope, actually there are two modes of operation. Okay, because the probe wire is scanned back and forth across the surface in a raster pattern, either in a constant height mode or in a constant current mode. So accordingly there are two modes of operation. Okay, and one more thing is the STM can only scan the conducting surfaces. Okay, the surfaces which are electrically conducting. Okay, because it rely upon the small tunneling current which is arising between the tip and the sample. Therefore, in other words, it cannot be used for non-conducting specimen or sample. Okay, now let us discuss the two modes of operation of the STM. So number one is the constant current mode. In this mode, a feedback loop maintains a constant probe height above the sample surface profile. Okay, and the up or down probe variations are being recorded. Okay, now it is actually most widely used STM mode, but it is comparatively slower than the constant height mode. Okay, and this mode of operation assumes a constant potential barrier across the surface through which the electron tunneling takes place, and there is no risk of destroying the tip during the scan. Okay, so in this mode there is no risk of tip destruction in the scanning process. So this is the imaging mode of your STM, the first one which is the constant height mode, and the second one which is the constant current mode. Okay, so here in the constant current mode the feedback is on, and in the constant height mode the feedback is off. Okay, so as you can see, this is a graph where we have taken the current I in the y-axis and the scan axis is your x-axis. Okay, so this is having a constant value. Okay, because it is a constant current mode. Okay, now this is the probe tip which is following this dotted line path. Okay, now this is the sample surface which is very much similar to the dotted line. Okay, but there is a gap between the dotted line and the sample surface, which is the gap between the tip and the sample. Okay, and it is maintained around 1 nanometer. Okay, so this is the constant current mode. Now the upper figure is the constant height mode. Okay, you can see here the dotted line is smooth, so the tip is maintained at a constant height and the sample surface is as it was in the second figure. Okay, so now if we measure the tunneling current, then in this case it will vary according to the scan axis. Okay, let us see the second mode which is the constant height mode. Okay, so in this case actually it is the fastest scan mode of the scanning tunneling microscope, and in this mode the tip is constantly changing its distance from the surface, and this is reflected in variation which is recorded by the tunneling current as the probe scans the area. Okay, and the feedback loop actually maintains the initial probe height and then it will be turned off okay, during the scanning process. And the scanning probe will provide a mapping of the distribution of atoms on the surface. But there is a disadvantage or drawback in this mode, which is actually there is a risk that the tip will bump into unexpected high regions on the surface and can be destroyed. Okay, so this is a drawback in this mode. Now let us see the resolution of STM. Actually STM is, as we were studying initially, it is having a very high resolution because the exponential dependence of the probe surface atom separation, suppose it is small d, okay, in the transmission coefficient, that is having a value around exponential of minus 4kd, okay, and hence in the tunneling current. So the tunneling current is very sensitive in order to change the separation, which is small d, and this makes the scanning tunneling microscope a very sensitive one. Okay, and the tunneling current actually depends so strongly on the distance that it is being dominated by the contribution which is flowing between the last atom of the tip and the nearest atom in the specimen. So it is having a very high resolution. Okay, now when we were looking at the figure, the schematic diagram, we were seeing that the tip is being held by a piezoelectric tube. So what is a piezoelectric material? Actually it is a material in which an applied voltage in one direction will make the element longer or shorter in the other direction. Okay, so the scanning tunneling microscope utilizes this piezoelectric tripod scanner, okay, piezoelectric tripod scanner for the fine control of the tip in all the three dimensions when it is near the sample or the specimen. Okay, and this piezoelectric tripod actually maintains the tip and the sample separation, that is small d, typically within 0.4 to 0.7 nanometer range, which is the equilibrium position between the attractive, okay, that is 0.3 to 1 nanometer, and the repulsive, that is less than 0.3 nanometer interaction. So in this situation the voltage bias will cause the electrons to tunnel between the tip and the sample, so that it will be creating the tunneling current. Okay, now the modern scanning probe microscope actually uses a tube geometry as shown in the figure. Okay, so it is using a tube geometry, and each of the four indicated sections can be made longer or shorter individually. Now you can see in this figure the first one, which is the piezoelectric material, okay, which we have taken in form of a piezoelectric tube which is connected with the voltage, right? Then come to the third figure. This one is the cylinder or the tube having the four sections, which is x plus, y plus, x minus and z. So each of these four indicated sections can be made longer or shorter individually. Now suppose if all these four sections are made longer or shorter at the same amount, okay, by the same amount we make all these four to be longer or shorter, then what will happen? The tip will move in the z direction. Okay, now if the positive x is made longer, okay, positive x side is made longer, and at the same time the negative x side is made shorter, then what will happen? The cylinder or the tube will be tilted, okay, it will be tilted to one side. So in this case what will happen? The small deformation will happen, and this makes the tip move primarily in the x direction. Okay, so the same can be done in the y direction also. Okay, so the scanning tunneling microscope, if we see, it can also provide the information on the electronic structure, okay, atomic structure along with the electronic structure at a given location in the sample by sweeping the voltage and measuring the current at the specific location. So this gives a plot of the local density of the states as a function of energy within the sample, and there is an advantage of this STM over other measurements of the density of states, which lies in its ability to make extremely local measurements. Okay, so it is having advantage in measuring the density of states. Okay, further advantages, these are here noted point wise. Number one, as we have seen, it is having a very high resolution. Okay, its resolution is around 0.1 nanometer, and it is very better than your atomic force microscope, that is AFM. Now number two, the tunneling current is very sensitive to the changes in the tip sample separation, that is small d. Okay, so if we change the value of small d slightly, then it can affect the tunneling current. Hence, the STM is a very sensitive instrument, right? Number three, the local density of electronic states can be measured very accurately by this STM. Then in the fourth point, the STM has an atomically precise positioning system which allows very accurate atomic scale manipulation. Okay. However, it has some disadvantages or drawbacks. So number one, it requires extremely clean and stable surfaces, and the tips should be sharp enough and excellent vibration control. Then sophisticated electronics are required, which is quite challenging and therefore difficult to maintain the setup. Okay, then number two, the STM, that is your scanning tunneling microscope, requires conductive samples and relatively conductive samples on a conductive substrate. Okay, so it cannot be used in case of your detection of non-conductive samples. Okay, and in the third point, the scanning is a very slow process. Okay, it is a very slow time taking process of imaging. Okay, now finally let us see some of the applications of STM. Number one, the STM can be used to investigate the discrete atomic like states of colloidal quantum dots and other systems. Then number two, it can be used to investigate the Coulomb blockade and Coulomb staircase phenomena. Then number three, in order to image and manipulate individual atoms in a sample, it can be used. Number four, it can be used as a spectrometer for measuring the electronic energies. Then number five, it can provide information on the topography and the defect which is produced in the surface. Okay, the defect structure of a surface over distances close to the atomic scale, because it has a very good resolution. Then number six, the atomic deposition of metals like your gold, silver, tungsten, etc. with any desired pattern can be made. Okay, then number four, it can be used for measurement of conductivity of long chain like molecules. Okay, now finally, one more thing I would like to say, the scanning tunneling microscopy, which I have taken from one book, and this is what I have taken from another book in which the STM is given in a brief manner. Okay, so this you can also read for your knowledge purpose, and you can prepare your note accordingly. Okay.
Thank you.